In our last lab, we were adding different types of compounds and mixing them into solutions that we were putting in ice and then freezing that compound like cyclohexane. And then we were looking at the change in the freezing temperature. So we had probes that were managing that temperature or looking at that temperature. We're going to use that change in the freezing point to determine the molecular weight of our compound. So if we're talking about atomic mass, obviously we're looking at atoms. If we're talking about molecular mass, we are talking about atoms that are grouped together, right? Why is this helpful? So what we can do here is, remember we were talking a few chapters ago about molarity, and if we know how many grams of material we have, that is also how many moles we have on the periodic table. So 12.01 grams of carbon is that many moles. And we can use this idea that we know that for every amount of grams we have that many atoms available. And if we do the molecular mass, if we start to add these together and add all of that up, we know how many molecules we have per number of grams. And we are going to use that idea then to think about how this changes the melting temperature. In order to do that, I just have a visual here to look at pure substances, which, if we have something maybe that is in solution, these things can organize themselves. So when we lower the temperature, so maybe this is a liquid and these things can move around and interact, but then when we freeze it, they can condense and they can make these crystal structures that form nice tight units, and they're able to do that more consistently as that energy is removed as we cool that system down. Now we're going to add a compound in here that's our unknown, for example, and that's going to interrupt those regular interactions, and it's going to change the freezing point because it takes a different amount of energy to break these bonds than it does if it's a pure substance. So that's kind of the idea of when we freeze something, those crystals, those things are forming in a different way, and different amounts of energy are going to be associated with that. And it's also going to depend on the concentration, the number of molecules or atoms that we put in that solution. The more we have in there, the more disruption there's going to be, and theoretically the more the change in temperature is going to move. This is the equation that describes that property, change in temperature, which is the starting point to the ending point. The change in that is equal to this freezing point depression constant, and that's going to be the solvent that we're using, like cyclohexane, or it might be water or some other liquid. And then multiply that by molality. It's not molarity. Big M is molarity, small m is molality. It's the number of moles per 1,000 grams. So it's per mass instead of per volume, which would be molarity. Similar idea. But we can use this idea then to rearrange this, and we can also then find the grams per mole, the molecular weight, will be equal to that constant times the grams of the solute, that would be, for example, the unknown, divided by the change in temperature times the kilograms of solvent, which would be the cyclohexane or our water. And we can solve this, we can plug these values in, right? We have that change in temperature, we can plug all of these values in if we recorded those in our lab notebooks, hopefully, and then we can solve for the molecular weight of our unknown or our compound, for example. And this is what allows us to determine the molecular weight. So again, the setup here is the Kf value for cyclohexane is 20.2 degrees Celsius of change times the kilogram of the solvent divided by the number of moles that were put in there. And that we plug these values in from what you determined on your notebook. The change in temperature, that's going to be, remember we did two different recordings, and then that's going to be the difference between where that inflection point for that freezing temperature, and that should give you the molecular weight of the unknown that you tested during that experiment. So the big thing is just to make sure that you're keeping the things, the solutes versus the solvents, that we have the proper units, and that you are solving this properly to cancel out the units and to get the number of grams per mole left over. In the second part, we've actually included another term, this I. It's the Van't Hoff equation. And this is going to include this term that is going to talk about basically how many pieces your compound maybe turns into. So if we're talking about a molecule, let's say it's something like an ionic compound, let's say sodium chloride. That's going to turn into two parts because the sodium is going to fall apart and the chloride is going to fall apart. So your I is going to be a 2. And sometimes things will just be solid. It will stay together. So that then would change that value. So that's the second part. We're really looking at this and how many different components we have between our different compounds. Does urea break apart, or does it stay solid? Remember, that kind of comes back to this idea where, how many actual pieces are in our solution is what changes the melting point. So if we have something that falls apart when we put it into solution, that'll change the melting point different than something that stays together. So that's that second part with this I is the Van't Hoff unknown, and that's what we're really solving for in that last part.